In my project, I attempted to use unsupervised Gaussian mixture modeling to classify a sample of young stellar objects solely based on their simple observational parameters. This data was originally presented in Furlan et al. 2016, which was the first presentation of the Herschel-Orion Protostellar Survey, a sample of 410 potential young stellar objects, hereafter referred to as YSOs, present in the Orion molecular clouds. The researchers in the original paper further narrowed this down to 330 objects, which had full Spitzer and Herschel data, and were unlikely to be non-YSOs. They classified these objects into four main types, and then applied several thousand model spectral energy distributions to determine best fit values for several parameters, including inclination, envelope mass, centrifugal radius, and others. These four main types are the object classes. Well, how are these classes determined? As YSOs age, they tend to deplete the material that surrounds them. The envelope tends to either be dispersed by the central star, or undergo infall and settle into the disk. The disk, meanwhile, tends to accrete and thin, eventually disappearing entirely in the process of planetary formation. We can generalize these stages of young stellar aging into classes. Class 0 objects have incredibly thick envelopes, and so their spectra are dominated by the cold, long wavelength emission of the outer envelope. Class 1 objects have thinner envelopes and pronounced disks, so we have a little short wavelength emission typically overshadowed by a lot of long wavelength emission. Flat spectrum objects have a flat spectrum. The emission from the star and dust are essentially at parity, leading to a characteristic flat shape. And finally, Class 2 objects are sufficiently dust deficient that the majority of emission comes in the form of black body radiation from the star, with a slight infrared excess from the protoplanetary disk. The two general parameters that you can use as rules of thumb to evaluate YSO class are the 4.5 to 24 micron spectral index and the bolometric temperature. The spectral index is a fancy word for what's the slope of the spectrum if we fit a power law, because a power law will always form a straight line on a log-log plot. So, the 4.5 to 24 micron spectral index is the slope of the line drawn between 4.5 and 24 microns, which gives you a very good sense of how the intensity of short wavelength emission compares to the intensity of long wavelength emission. The bolometric temperature, meanwhile, is the temperature of a black body that has the same mean wavelength as the spectrum. Think of it as an estimate of the temperature of the material at an optical depth of tau is equal to 1. So obviously, something like a class 0, where you can only see the thick, cold envelope, has a low bolometric temperature, while something like a class 2 will have a near-stellar bolometric temperature. Knowing these two parameters, we, as the researchers did, can make estimates for the classes simply by plotting and drawing some lines. For example, in this plot, you can generally assume that a class 0 object would be cold and would have a very positive spectral index. Something closer to class 1 might be warmer, but still has a positive index. A flat spectrum source is defined as having a flat spectral index, so it would be close to 0. And a class 2 source would be hot and would have a negative index. This seems obvious to us, especially because I just explained it all to you. But what if we fed this information into a GMM classifier, which doesn't know anything about anything that I just said? It just understands the numbers and that's all. What will it determine? Well, that's what I tried to find out. The three observational parameters in the dataset that are not completely useless are bolometric temperature, bolometric luminosity, and the spectral index. Just plugging those in, I was genuinely shocked by how good the GMM classification was. At this point, the only major issue was that there were so few class 2 points in the dataset that the classification could not successfully differentiate them. Thus, I had to settle for only picking out class 0, 1, and flat objects. We can also plot bolometric luminosity against the other two parameters, which generally does not correlate. I also attempted some more simple classification methods, but none were very different or showed any interesting behavior. What was more interesting was extracting the actual classification from the 2016 paper, which for some reason was not actually given a figure. I don't know why you would classify a bunch of stars, but then never bother to actually demonstrate the classification itself. Anyways, we can clearly see that the researchers' methods literally color inside the lines much more closely. there is also evidence of the correctly identified Class 2 objects. And when we plot these points relative to bolometric luminosity, again, there is very little correlation, but one can clearly see how the classes are divided based upon their bolometric temperatures and their spectral indices. Finally, I did some Python trickery to produce a plot that highlights the disagreements between the two methods in blue. As we can see, the main points where GMM and the original paper disagree are the fine boundaries between the groupings. I would argue this isn't all that bad, isn't that terribly incorrect, because the classes are naturally in this state of potential overlap, as the stars are aging and constantly transitioning between the classes. We can also see that, obviously, GMM could not identify a single Class 2 star, and that it also struggled to identify cool, flat sources as flat, rather than as Class 1. Overall, however, I was shocked to discover how accurate this rather quick and rough GMM classifier was, when it comes to facing off against literal, manual evaluation of objects by a team of expert scientists. If we tally up all the matching evaluations, we get an 82% success rate, and this is after letting the machine do all the work and doing no manual evaluation of SEDs or any other data points. I am typically extremely skeptical when it comes to machine learning, but the fact that unsupervised basic machine classification is this effective possibly changed my outlook on it. The jury is still out, however.